Hello, everyone. My name is Thomas Kosch, and it's an honor to share the session 5 today, which is the last session of today, with the title Touch and Typing. And we have 3 very thrilling and excellent talks today, which I'm honored to chair. And we will start now with the first presentation with the title Stepper, Swipe, Tilt, Force, Comparative Evaluation of 4 Number Pickers for Smartwatches. And this work was published by Yuan and Ahmed, Sabbir, Arif. And with this, you can start to present.
Okay. Hello, everyone. My name is Ahmed Arif. I'm an assistant professor of computer science at the University of California, Merced, where I lead the Inclusive Interaction Lab. Today, I'm going to present a work led by my PhD student, Yuan. She wanted to attend the conference in person to present the work herself, but she has a more pressing matter to attend to. A couple of weeks back, she became mother of a beautiful, healthy baby girl. So please feel free to send your well wishes her way. Smartwatches are becoming increasingly popular. A recent survey showed that in 2021, 1 in 5 US adults regularly wore a smartwatch, while market research indicated that global demand for smartwatches increased by 20% in 2020 and about 40% in 2021 compared to the previous year. Nevertheless, interaction with smartwatches is difficult and limited to notifications on emails, text messages, and social media feeds, mainly because of the smaller screen sizes. Text entry and number entry is particularly difficult on these devices because of the smaller key sizes, which makes precise target selection difficult and error-prone. As a result, number picker has become one of the most dominant input tasks on smartwatches. Unlike a traditional text entry technique like a keyboard, number pickers display a default value on the screen, then allows users to adjust the value to an indented value by incrementing and decrementing it using a 2-segment control. Just to illustrate its dominance on smartwatches, modern Apple Watch comes with about 40 pre-installed applications. 28 of them are only for acquiring and viewing information, 8 of them, which results to about 20% of all applications, support number entry using a number picker, and the remaining 4 applications partially support alphanumeric text and emoji entry using keyboard or similar approaches. Input stepper is the default number picker on most smartwatches. When users tap on a numeric value, it displays a full screen virtual number wheel containing all legal values. Spinning the wheel by flicking up on the screen increases the value, and spinning the wheel by flicking on the screen down decreases the value. The pace of the increment and decrement is determined based on how fast users click on the screen. Faster clicks rotate the wheel faster, and slower clicks rotate the wheel slower. When the desired number is displayed, users pick it by tapping on it. It's possible to continuously spinning the wheel to some extent. It's not fully supported because for continuous spinning, users have to continuously tap or flick up and down on the screen, which requires quite a lot of tasks. Once flicked, the wheel keeps on spinning for some time and gradually slows down to a full stop. So there's no other way but repeatedly clicking on the screen for continuous spinning. Waiting for the animation to start. Okay, there you go. The swipe-based speaker enables users to pick numbers by performing swipes. This is a new approach we improved or developed based on the default approach. It's quite similar, but there are some subtle and significant differences. With this approach, tapping on a numeric value activates an invisible number wheel containing all legal values like the default method. But with this method, users can swipe up and down on the screen to increment or decrement a value. One difference between the default input stepper and swipe is with the default stepper, users perform a short quick click, while with the latter, the method we are proposing, users perform a steady swipe. And a single swipe changes the value by 1 unit. The length of the swipe can be short. It doesn't have to be really long like the default method. So this could be micro gesture to up and down to increase or decrease the value. Users can also activate continuous spinning of the number wheel by stroking and holding the swipe for 850 milliseconds. Lifting the finger deactivates the continuous spinning. This allows the user to actively decide when repeated spinning is needed, especially when the value is too large or too small than the one displayed on the screen. The pace of the spin, in contrast, is determined based on the length of the swipe. If the user swipes long and then holds the swipe, then the spinning wheel is going to spin faster. But if the user performs a short swipe and then hold the swipe, it is going to increase or decrease much slower. The tilt-based method, on the other hand, enables users to pick numbers by tilting their smartwatches towards or away from the body. We're interpreting tilting down and up. So up means tilting away from the body, and down means tilting towards the body. Tilting the device once, then returning to the initial position changes the value by 1 unit. For continuous spinning of the invisible number wheel, users can tilt and hold the position for 850 milliseconds. That activates continuous spinning of the wheel. Unlike the previous one, where gesture was the determining factor of how fast the wheel is going to spin, for this method, it's reliant on the angle of the tilt. If the person or user tilts, tilts more towards the body or away from the body, the values are going to decrease and increase at a faster pace. The force-based approach, which is the third new approach that we are proposing, changes the level of force on the screen. And the user can change values by variating the force on the screen, and increasing the value could be performed by increasing the pressure level on the screen, and decreasing the value can be performed by changing the touch force from regular to a lower value. Changing the level and lifting the finger deactivates the continuous spinning, which is activated after holding a specific pressure level for 850 milliseconds. This method uses a temporal approach, unlike the approaches we used in the past, the last two methods. Unlike using a specific gesture for continuous spinning, this method uses a temporal approach, where holding a specific level of force longer increases or decreases the value faster, and this rate changes every couple of milliseconds. So for 600 milliseconds, the value is changed 1 digit, then for 2 seconds, and then 1 digit for 200 milliseconds for 5 seconds, and then 1 digit for 5 milliseconds. So the longer the person holds the pressure, the faster the spin, the faster the wheel spins. We conducted multiple studies, and it's impossible to present all these studies here in this talk, but I encourage you to read the paper where we have presented numerous studies on how we mapped various force levels and tilting and gestures to the wheel interactions. The first study we are reporting here compared seated and walking condition. The purpose was to find out that whether there's a difference in performance between these three methods compared to the default method in these two settings. We had 12 participants within subject design. 2 settings were counterbalanced. The 4 methods were also counterbalanced. We had 15 random 2-digit values that were shown on the screen, and users were instructed to change it to the value that is displayed above it. So altogether, we had over 1,000 numeric values, excluding practice values. In the user study, we used an iPhone X for mainly for the pressure sensors, because we want to implement a force-based approach, which was not possible with current smartwatches. We developed a custom application using the default SDK, and it simulated Apple Watch display on the phone display. We made sure that the surrounding areas of the phone was deactivated. They were not touch sensitive, which made sure that there's no accidental touches during the study. We used a wristband to hold the phone like a smartphone. We used a treadmill to simulate walking. The treadmill was set to on 1 mile per hour. This value was selected based on some prior studies that show that mobile users tend to walk at this speed when they're typing and walking. We calculated both quantitative and qualitative metrics. We calculated task completion time in seconds, which was how much time it took to perform a task. We also calculated action per task, how many actions were taken to perform a task. And we collected NASA TLS questionnaire and some usability questionnaire. Study results were quite interesting, actually, because we found out swipe-based method was significantly faster than other methods in both stationary and mobile condition. This is most probably because swipe took fewer actions than other methods, but not quite, but still the actions were performed much faster than others. We also found out that there is no significant difference between mobile and stationary condition, which is surprising because previous studies reported a difference when some approach was used in mobile settings and stationary settings. But this could be because of the lower walking speed we used in the study. So we recommend caution in interpreting that result. Qualitative data was also interesting. Participants found the default picker and the swipe-based method substantially faster, more accurate, easier to learn and use, and were willing to use these methods in both stationary and mobile settings. They also found the default picker and the swipe-based method to be the least mentally and physically demanding, as well as least frustrating. We wanted to explore a little bit more about the usability of the new methods. So we developed an approach to enable number picking within text. So we are calling them inline number picking. And this is mainly because the default number picker displays the numbers in full screen, which is not really useful when you're trying to respond to a text messages or the context of the message is important. So we tried to implement something like this, where there's a magnifier that kind of maintains a distance between your fingertip to make sure that the fingertip is not covering the magnifier. You can see the number changing within the magnifier, so it enables performing the task with some visual feedback. And we will conducted another study to find out that whether there's any difference in terms of performance when users are performing inline operations. We conducted a similar structured study, only the methods were different, but the metrics and the procedure were the same. And the results were quite interesting again, because we found swipe-based method again was significantly faster than the other methods in both individual and inline condition. And as you can see that it also requires fewer number of actions. We found out that the overall, compared to the first study, users took a little bit more time, which is not unusual because of the visual scan time. They have to visually scan for the numeric values and so forth. The qualitative data was also similar to the first study. Participants found the default picker and the swipe-based method significantly easier to use. They also, like the previous study, found the default picker and the swipe-based method to be least mentally and physically demanding and the least frustrating. So in summary, we found out that swipe-based methods were significantly faster than the other methods in both stationary and mobile settings, and with individual inline numeric values. Participants found the default picker and the swipe-based method significantly easier to use in both studies. Participants also found the default picker and the swipe-based method to be least mentally and physically demanding than the field-based and force-based method in both studies. So what are the design recommendations and takeaway? We recommend using hybrid of input stepper and swipe to enable selection of numbers with short edit distances with clicks and long edit distances with swipe and hold gestures. We also recommend automatically slowing down the spinning rate when the number reaches a probable value, which most probably is going to be easier to select. With this, I'm going to complete my presentation. I'm happy to take questions.
Thank you so much for the excellent talk. So let's give Ahmed a round of applause. Thank you so much for the talk. Are there any questions in the audience? And for those who attend virtually, just don't hesitate to post your question into the Zoom chat, then I can refer them to the speaker. Nobody likes smartwatches? Well, I do. In the first example you have shown, we have showed that typing on a keyboard using characters is something that is quite challenging to do on smartwatches. But then still you focused in your research on picking numbers. How do you believe does your approach transfer to typing characters on smartwatches? Do you think this is possible, or don't you think that it's like more difficult to achieve?
I think it's possible to enter text on smartwatches. So that's a different line of research that my laboratory and my students do. But I'm not sure that whether traditional keyboards are going to be effective there. So we need some alternative to enter text on smartwatches. Number picking obviously is not going to be, a similar approach is not going to be useful for characters because we have too many characters in different languages and English as well. But some studies showed that gesture typing, when you're performing the gestures, connecting the letters, that can yield quite good entry speed when you have a very aggressive predictive system. But it's still difficult to enter one character at a time. So the speed is slower. If you aim for accuracy, the speed is slower. If you aim for speed, then it's more error prone. So that's the Goldilocks we have here. But yeah, I mean, I think it's possible. In theory, I think it's possible, but we haven't found the holy grail yet. I think we have to wait and see that what approach works in such a scenario.
Thank you so much. And we got one question in the Zoom chat. Actually, two. I will read out the first one, and maybe afterwards you have time to answer the second one in the chat, which is from Mark Hancock, who asks, I noticed that you haven't considered the dial on the side of the smartwatch in your work. If you did consider it, how do you think it will perform compared to swipe or the stepper method?
That's an excellent question. For this study, we did not consider the dial. But I think this could be quite good, especially for people with motor impairment, because they have a physical, dial that they can hold, and would be easier than just performing, precise selection or any kind of selection approaches on the touch-based device. I think it's going to perform. I speculate that it's going to perform better than what we have here, but this is just a speculation based on my understanding of the system. But the reason we did not look at that, it's because many watches do not come with the crown. The smartwatch that we used in a laboratory for preliminary design, those did not come with a crown. But I agree with you that if you're suggesting that a crown is likely to be more precise just because you have physical reference to that. If you have a little bit of tick sound when the crown is moving, it's going to be even better because you get a bit of haptics and at the same time auditory feedback with that. I hope that answers your question, but at the same time, this is just speculative question answer to your question.
Thank you so much, Ahmed. So let's give Ahmed another round of applause. Thank you so much.
Thank you.